Another important relationships which I had told that people always ask in fact this question I get asked every time I teach a short course is what parameter of vibration should we measure? Is it displacement, is it velocity, is it acceleration? Well, to answer this question, if I look at x, it is capital X, the magnitude of the displacement, magnitude of the velocity is omega x, and magnitude of acceleration is omega square x, where omega is the rotational frequency in radians per second, where omega is equal to 2 pi f. F is the frequency given either in cycles per second or in hertz, which stands for. Okay. But you will see at high frequencies, because of this omega square term, there is a large quantity at high frequencies. So, it is always advisable to measure any high frequency vibration as acceleration, and low frequency like a shaft rotating at less than 1 rpm, 2 rpm, to just to measure the static runouts or dynamic eccentricity, etc., we can measure displacement. And intermediate, so the rule of thumb is sometimes 0 less than 10, so 10, and if the any frequency greater than, so this is for x, this is for omega x, and this is for omega square x. There are of course standards which also say whether you should measure displacement or velocity or acceleration. This is something you have to keep in mind as to what kind of response has to be measured and has to be determined from mechanical systems which are vibrating. So, this equation of motion is actually a second order differential equation. But I should tell you something more about this equation, in the sense there are certain terms which we can denote here. This is the right hand side is what is known as the forcing function, and you will notice this omega here, omega is nothing but the forcing frequency. So, if a machine is running at say n rpm is its operating speed, then this omega is equal to 2 pi f, and this f is nothing but n by 60 rotations per second or hertz. So, usually this is how this omega is related to the speed of the machine, and in condition monitoring literature people usually denote this as 1x frequency, nothing but n by 60. Okay. Harmonics of it will be 2 times, 3 times, and so on. So, this is the response. Now, this response x which I will measure would be of this form, sin omega t minus certain phase difference. So, this is the equation to the response, and this is a steady state response. Because you would appreciate that this system which has been represented by this equation we will have a response. But where is the energy coming to generate this response? It obviously has to come from this forcing function. So, that means if this forcing function was not there, if the right hand side was 0, I would not have a steady state response, but I would, if for some instance if the right hand side was 0, that means there is nothing to excite it, and if there was a small disturbance to the system, it would actually have certain oscillations and which would damp out because of the damping present in the system, and such a response is known as the transient response, as opposed to the steady state response which I have written here. Okay. But in condition based maintenance, we are actually interested in the steady state response, because we would like to see how the machine behaves when it is being running at certain operational speed and what happens to the response. But then there are certain characteristics of the machine which are present, whether you have force or you do not have force, and this is actually depends on the coefficient, and one such very important is the rotational natural frequency given by over k by m, or frequency, the natural frequency is 1 by 2 pi root over k by m, and this is known as the natural frequency of the system, or the system which is vibrating, and this is an inherent characteristics of the machine or the system, and which is not going to change no matter what your forcing frequency is. But there are many consequences of this. For example, in one case we have the forcing frequency omega when it is equal to omega n. So, we will have a strong case of resonance, wherein there will be large motions of x, or the displacement. So, this has to be avoided while designing the machines. So, machine designers avoid resonance conditions during operation of a machine. Okay. So, we are supposed to not operate the machine at its resonance frequency. So, people always, designers tell the safe operating speed of a machine such that the resonance conditions are avoided, because once we have resonances, there will be large motions and which will lead to large fatigue failure and finally a catastrophic failure of the machine.